to do drops bouncing on a soap film, which is something that you'll see. These are sort of like research problems. After the first one, they're sort of research problems, but they're the sorts of problems that one can solve if you know what you guys have learned in the course. Okay, so here again we're looking at the rapid spread of something on the surface. This is, I think it's a surfactant, but you can see the front spreading very quickly. So, owing to the difference in.
Can you play it once more? It looks like there's a very strong difference between the first instance and the second.
Yes, it's definitely slowing down, but we should be able to predict how. And so that's one situation. That's a very thin film. And you can also, we're going to look at lenses today. So what happens when you have, we've all seen this when we make our salad dressings. We have something which has intermediate density between air and water, so it floats at the surface. And so related problems are de-wetting. So if you wet a surface with a thin film, depending on the wetting properties, the film might not be happy to be there. And so if you poke a hole in it, then it will basically spontaneously clear. And so this is sort of the opposite of the spreading problems that we looked at in the last class. Yeah, it's a film of fluid, it really doesn't want to be on the surface. So if you poke a hole, then you'll get this. The hole will spread. That's sort of like the inverse problem of what we had before, which is putting down a drop of fluid that wants to be on the surface, and so it spreads going to the S, right? But now S is basically changing sign, so you poke a hole and.
That would mean that the contact angle would be greater than 90 degrees.
Yeah.
The irregularity of the shapes have to do with the roughness of the surface?
Probably.
Can I mistake a circle, right?
Yeah. And also there might be something irregular in the. And yeah, another thing. Yeah, it might just be irregularity in the initial disturbance. Although, yeah, it's probably a combination of both, I suspect. And right, so so we've seen drops bouncing off hydrophobic solids. So there's no reason why you can't do the opposite, right? So here is we're going to have a solid hydrophobic sphere with density greater than water impacting on water. So if you submerged it, it would sink. But the energetic cost of wetting it is so high that the thing doesn't want to be there. So it will actually float, again, just like these water-walking creatures do, despite the fact that they're heavy relative to water. Okay, so okay, we don't need that anymore. We're going to need this. We're going to need this. Okay, so we're going to look at this today. Basically, what happens when we have a third phase of fluid at a air-water interface. So Okay, so first we have a pendant lens. So the configuration is going to depend on the three densities in the in the system. So the first one, you have something which is heavier. So we have a heavy lens of heavy fluid sitting on water. So this is phase C, A, and B. And so here we have rho A is the smallest, rho B, rho C. So this is heavy, it wants to sink, but surface tension can bear its weight. And so if we have the three tensions, AB, then we can have, so they're going to be basically two different capillary lengths based on the density differences here and the density differences here. Remember, the capillary length has G prime, so square root of sigma over delta rho G. We've said rho G because we're looking at situations like air, water, where rho of water is much greater, but it's in general rho delta rho G. So if we call this up and down, then we have L up, sigma AC, rho A minus rho C times G. Okay, and we know this guy is only going to be stable this thing is only going to be stable if the drop is small relative to the capillary length. Because if it's small relative to the capillary length, then its weight can be supported by surface tension. Okay. Similarly, we can trap something which is light at an interface. So here, the lightest thing around is the third phase. So say a helium bubble at the interface of water. So okay, and so these, so okay, so these are stable. So again, whichever capillary length you want to choose. Okay, and then this case is slightly more stable. Of course, this thing is just at an intermediate density, and so it's going to spread to some extent, which is going to be determined by these three surface energies. Sessile, sitting on top of. Okay, so this is basically what we saw in the video. We there poured oil onto the surface of water. So this is rho A less than rho C. So again, the third phase now has intermediate density. So we get some situation which looks roughly like that. Okay, and so as in the case of the puddle, which we considered at the very beginning, you basically have, despite my drawing, you have this flat region in the middle, and then you have basically this length where the thing matches, and this characteristic scale is the capillary length. So again, you can define two different capillary lengths according to the different density differences between the three phases. Okay? But this is basically L cap, and this is flat in this region. Okay. Okay, so you have stable drops, or I should say stable for lenses of any size. Okay, so let's look at so in this so we're going to get into the oil on water in a second, but again, whether or not this thing spreads is going to depend on the spreading coefficient, so the relative magnitudes of these three tensile forces. If S is greater than 0, the thing is going to spread indefinitely until you get a layer of molecular thickness. Benjamin Franklin, who you recognize from the American $1 bill, was interested in surface tension, and so he looked at this problem, which we mentioned earlier. And so if S is less than 0, then it's going to spread to some stable configuration like this. So this is basically what you get when S is less than 0. Okay, and so now, so what actually happens, let's actually look at a physical problem, which is an oil spill. So we dump some large volume of oil onto the surface of water. So how can we predict its spread of the radius as a function of time? How long do people have to respond? Okay, so last time we did some general scaling for gravity currents, which we'll be able to use here. So the first phase is inertia versus gravity. So again, if it's a large volume of fluid, its spreading is going to be resisted basically by its own inertia. So imagine we have a circular spill, depth h, radius r. We want to deduce r as a function of t. So let's call this rho plus delta rho. This rho, so it's the density difference which is causing the spreading. We of course have gravity. And we dump a volume V naught into the ocean. Okay, and so as we saw last time, the balance of gravity and inertia gives us that U goes as square root of G primed H, from which we can deduce the dependence of radius on time. Okay, where G primed is the reduced gravity, so it's G delta rho over rho. Okay? So that's the first phase. The second phase, viscosity kicks in. So it gets thinner and thinner, so the Reynolds number goes down, and then eventually you have some shear within the layer, and the associated viscous dissipation is that which resists the spreading. And as we saw last time, so last time we considered a fluid volume spreading over a solid, so you'll get a little more viscous dissipation. So the details of the flow are going to be different, but in terms of the scaling, it's about right. You still get velocity gradients over that sort of length scale, right? So you get V naught cubed over nu to the 1/8. So this was the scaling we got from we were considering the pancake problem, but the same applies here. Okay, and so now you get into the final stage where things are driven not by gravity but by surface tension, by this imbalance at the contact line. Okay, so we extend the scaling will again change. What do I call that? Phase or stage? Phase 3. Okay, so this depends on magnitude of S. So as we've seen here, if S is less than 0, we get an equilibrium. And of course, that's going to confine the spreading, right? If, on the other hand, you have a positive spreading coefficient, then that thing is going to go all over the shop. So it basically goes until it forms a layer of molecular thickness. I think I told you this story, right? About Benjamin Franklin. If you'd asked the right question, he was interested in surface tension, so he's looking at this problem. He's looking at its ability to suppress waves, but because I think he used a teaspoon of oil or something and put it on a pond and looked at, so from the spreading radius you could then compute the molecular size, and at that time the molecular size was not known. Franklin, 1760. So you may be looking at the right problem but asking the wrong questions, right? Okay, so that's good writing there, molecular thickness. Okay, so let's imagine this is a case. So we're looking at the case of indefinite spreading. So So phase 3A. Okay, so you imagine we're in a situation where the lens is spreading due to the positive spreading coefficient, but there's basically some shear within the lens, and the associated viscous dissipation is resisting the spreading. And so we saw that last time, the scaling in this limit. So characteristic viscous stress if this thing's spreading at a speed u. So have you guys ever seen so many scaling arguments, by the way? But they're really powerful. I mean, if nothing else, I want to convince you this. And you actually only come to believe them when you really are comfortable with the subject, right? When you've solved enough of them, you say, oh, yeah. But I remember when I was a student, I did, tons and tons of math to figure something out. And then at the end, I was like, Then I figured out the scaling argument. It's kind of nice to do it after the math, but sometimes it's better to do it instead of the math. Okay, so this is the balance. So this is the tensile force along the edge of along the perimeter of the lens, and this is the characteristic viscous dissipation. So looks like S over mu H, and then we can use continuity, S over mu V over R squared, right, because okay, so you get SV over mu to 1/4. So this is what we got last time when we were looking at spreading of a solid, spreading of a fluid over a solid. Okay, so we're going to get this 1/4 scaling, and there's an additional phase here, spreading phase. So we'll call this phase 3B. So now the principal viscous dissipation happens not inside the lens but outside the lens, so this doesn't have an analog. I suppose it could for spreading on a solid, but we didn't look at it last time. And there's, okay, so okay, so here you're really, the thing's in its dying stages, so it's really very thin layer. And so as it spreads in response to S, you basically get a growing boundary layer. So, right, so you're getting this boundary layer which is thickening And it's dissipation in this layer rather than this layer, simply because it's much larger, I suppose, is going to dominate the resistance. So this boundary layer, I think we've seen this before, Blasius boundary layer grows like square root of time. Look at that. So let's call this delta of t, the boundary layer thickness, goes like square root of nu t. So that's the Blasius boundary layer. Okay, so the scaling then looks as follows. Mu u, so this characteristic viscous stress is now based on the lower boundary layer thickness. And of course, this is going to be the viscosity of the second phase, pi r squared. So I should call this, let's call this water. S 2 pi r. So this is okay. So it's okay. Yeah. Okay, sorry. R squared goes as S mu nu square root of nu to the 3 halves. So we get R goes as S over mu. T to the 3/4. Okay, so you may think this is all very far-fetched, but if you look at data, there's a book by Fay, who's a professor at MIT, who was in engineering, and he has a very nice plot, and it's for basically the radius of an oil spill, and you really see all 4 of these phases in the scaling, right? So how the scaling's gone. We've got this. Well, it went. But it basically, you see all 4 of the phases. Right, so you see the distinct regions. Well, actually 3A, 3B, right? 3A, 3B. So this is R as a function of time. Okay, so just in case you think all these scaling arguments are patchy, they're good enough for me if they collapse the data, right? Question? No. Okay, so the next thing, so I want to show you a quirky problem that we looked at, which is kind of related to this, but this is about as quirky as it gets. But basically this professor, this colleague of mine, I shouldn't, I'm being filmed, showed us, was kind enough to introduce me to this problem. So here's the problem statement, right? I think I might have showed you a video of this earlier in the class. We basically put an oil drop down on the surface of water, and you expect it to either spread indefinitely or spread to some critical value. But this thing, so it's basically mineral oil with some quantity of surfactant. It basically goes. So we call this the beating heart, and it took well, let me see, I arrived at MIT in 1998, so it took me almost 10 years to solve this problem. But this is it. So this is shown to me by my senior colleague Harvey Greenspan. So basically, he showed me this thing. So it's a lens on water, and it's just spontaneously beating, right? And what is going on? And so it's a very quirky problem, and you may say, why look at this? But I think it's very interesting for a number of reasons. There's nothing wrong with doing curiosity-driven research, of course. But this was actually first looked at.
It has two different contractions, right?
Yeah, exactly. It seems to spread slowly and then snap back very quickly.
It snaps once and then snaps again, and then it seems so.
Yeah, it's a little bit irregular too. Yeah. So, anyways, I hope you agree with me. This is at least an interesting and strange problem, right? And so the sort of you get 20% contraction. These things, you can do it with lenses as large as this, a couple of inches across. But so this was first reported by this guy Buchli, who was a professor of zoology at the University of Heidelberg. So investigations on protoplasm. So he was interested in finding mechanical analogs of biological systems. And so this was his analog of the heart. So I don't know how he found this, but he was interested in, and this was then looked at by a chemist, Seba, around 1980. And I like Seba's quote, right? The ultimate goal of physiologists is to be able to explain living behavior in terms of physico-chemical forces. Thus, any expansion of our knowledge of such forces based on inanimate systems should be examined to see whether this might not offer insight into biological behavior. So this is, again, in the same spirit as Buchli, trying to understand mechanisms that can give rise to oscillations, right? And there are many biological systems which have periodic behavior. So you have oscillations of cells and nerves and muscle tissue, oscillations in mitochondria, and you have biological clocks. So how do biological clocks work? This is a way of basically imposing periodic motion from pure chemistry, right? Okay, and so so conversion of chemical into mechanical energy is one of the main processes in biological movement. So chloroplast movements and muscle contraction, and of course, this is all good to use as motivation in hindsight, but I just thought it was kind of an interesting, quirky problem. And so, so how does it change with surfactant concentration? That's the first thing you can ask. So it turns out the edges will actually shatter. You can see this happening here. If you increase the surfactant high enough, the thing will actually explode. So it's a sort of a spontaneous emulsification. So this is a way that you can break up a fluid volume simply by changing the chemistry. So it really does explode there. But what we'll see is that this is happening on a smaller scale, even in the stable beating configuration. Okay. And so, all right. So the experiment. So again, I was shown this problem. I said, okay, well, let's really take a look at it. What's going on here? So we basically looked at this mineral oil, and this is so we have a non-ionic surfactant which is insoluble in water. So it never goes in there. So the surfactant which is in the drop either stays in the drop, it can go to this surface, and so we think things are not so bad. So we put the thing on the surface with an eyedropper, and it doesn't depend on the depth of the water. It does depend on the surfactant concentration that we've seen. So if we put in no surfactant, you just get a sessile lens, a stable sessile lens. If with moderate surfactant concentration, you get the steady beating, and for higher surfactant concentration, the edge becomes frayed and it releases droplets, and at the highest concentration, the thing explodes. And so, but a key observation. So I thought I'd figured this problem out many times, but they were all false dawns. So so the other thing we saw, you noticed, you had a sort of slow expansion, then it would snap back quickly, it would appear, right? And the other thing was that the odor of turgitol, which is a surfactant, was in the air. And I didn't even know before this that surfactants could evaporate, okay? So when I thought I had figured it out, my senior colleague goes, but watch this, and he put a lid on the container. He put a lid on the container, and it stops beating immediately, right? So from that, so you put a lid on, the thing doesn't beat anymore. So from that, we concluded that evaporation is critical to the dynamics. And so we measured and sure enough found that this surfactant, so the surfactant in the drop can not only, so it can stay within the drop, but of course it wants to be on interfaces. So it wants to be on that interface, or it can survive there, or it can evaporate. Okay? So the fact that it can evaporate from the free surface gives a possibility of, so if the surfactant is evaporating from there, you're getting less surfactant, which means higher surface tension, which will give rise to this slow spreading, right? So that'll give rise to the slow spreading. The other thing that will give rise to the slow spreading is emplacement of surfactant onto this lower interface by diffusion. So if you have a fluid with a surfactant, the surfactant is going to want to go to the interface, so it'll slowly emplace there. So that's what happens here. The surfactant comes down, hits this interface, decreases the surface tension. Meanwhile, the surface tension here is increasing because of evaporation. So the two effects are both leading to spreading of the lens, right? Okay, so we measured the evaporation rate of turgitol, and it was low, but it's critical. And so what is going on here? So we have this slow expansion phase marked by the evaporation of the surfactant into the air, which increases the surface tension there, right, causing it to spread. Similarly, emplacement of surfactant at adsorption onto the lower surface decreases the surface tension there, again causing the lens to spread. Right? And then the question is, so it's fine that it's growing, but why does it snap back? Right? So it snaps back because basically all of a sudden this interface just dumps a ton of surfactant onto the surface. Okay? And you say, well, why is that? But you can see that it would work, right? If we can somehow, if we have this picture and then all of a sudden, every once in a while, this thing just spews a bunch of surfactant onto the surface, that'll decrease the surface tension there, so it will snap back, right? So that's actually what's happening, but let's see why. So to see why an instructor in our department who's working with me at the time, Roman Stalker, who's now a professor in engineering, did these experiments, so you can actually see waves. This is the edge of the drop, and you see waves coming along and dumping. You see them? Dumping stuff onto the interface. So this is an inverted microscope. So this is, again, the bottom of the drop. This is the edge of the drop here, and you'll see waves coming parallel to the surface and dumping stuff onto the surface. And this stuff they're dumping is surfactant, so that, you see it there? So you see both the fingers and these waves, and this is happening even in the case where you just have the steady beating. So you get this dumping of material that decreases the surface tension, and so it causes the thing to jump back. And so where are these waves coming from? Right? Yeah. This is the next question, right? But in any case, we've seen these flushing events. So there's all sorts of chemistry that we're not too interested in, but we see this sort of spontaneous rupture as these waves sweep along the base and break. So where are these waves coming from? So to begin with, another clue in sorting this out was the circulation within the lens, and you can see it actually in this flat. So again, this lens is basically flat for most of it, and there's no circulation there, but in this region with the corners along the edges, there's a circulation which looks like this. Okay, so why is that? That has to do with the fact that, again, we're getting surfactant absorbing from the bulk into the lower surface, right? But because you have a corner here, there's going to be less surfactant available to absorb onto the surface. So this part is going to get more than this part, right? Which means that there's going to be relatively less surfactant here, which means higher surface tension. So you're going to get a Marangoni stress, which drives this large circulation, which we saw, right? And it's only going to happen in the corners in the edges because of this corner geometry. In the central region, which is flat, you'll have uniform surfactant concentration.
So in the corners, the surfactant is passing to the water. That's what you said.
No, in the corners, no, it's always in placing onto this lower surface, right?
Okay.
But the point is, you get into a corner, which looks like that, and you're soon going to run out of surfactant, right? So it's the same sort of argument. It's a question of surface area to volume ratio, right? Yeah. And so this is indicating that the geometry in the corners is giving rise to Marangoni stress. So now we have a Marangoni shear layer, right? Right? So we basically have a Marangoni shear layer, and if you remember in the tiers of wine, we saw that these can go unstable to two different types of instabilities. One is longitudinal rolls. So if we have a layer, well, let's use this geometry. This is our layer of wine, and this is our surface tension gradient. Then we can get rolls like this, or you can get waves like this. Okay, and so what we're seeing in this problem is waves like this, and it's consistent in terms of the parameter space. And these waves are actually breaking. And it's these breaking waves associated with this Marangoni shear layer, which is dumping surfactant onto the surface and causing the lens to snap back. Okay? Okay, so again, we have a Marangoni. Yeah, so this is basically a zoom. This is what's happening here. You basically have a Marangoni stress, so you have a very high shear here, right? So you have high motion, high speed here, and this shear in this region is then giving rise to waves which break. And these guys show that whenever a Marangoni shear layer with a free surface is, with an interface is virtually always unstable. Okay, so everything's consistent and it seems to work, and so we were able to predict the frequency of the beating heart. So a quirky problem, if ever there was one. And here's an even quirkier one. So this is done by Bud Holmesy, and this is another surfactant-induced auto-oscillation, right? So a sort of spontaneous periodic motion. Again, I think I might have showed you this one. So here you have a drop just pinching off on the left, and here you have something. So there's a surfactant in here generated by chemical reaction at the surface of the drop in the ambient fluid. And so after the thing dumps its first drop, it starts spontaneously spewing micro droplets. I love these problems because they're incredible. You have to throw everything at them, right, to figure them out. I mean, that last one was awful. 10 years. Yeah, this one is worse. It's so bad that I'm not sure that I either understand or believe their answer. But
that's real time.
yes, no, it's slowed, I think. But yeah, so here, very simply, what on earth is going on?
I don't even see it slowing down the speeding yet. I mean,
No, it seems to be pretty happy doing what it's doing. But you basically, the surfactant is, yeah, I'm not really entirely sure what is going on in this one, but it's certainly quite striking. And so, so their explanation. So what's their? Let me see if we can understand their explanation here. So you have water and hydrochloric acid, and oil and linoleic acid. So there's some chemical reaction which gives rise to surfactant on the surface of the drop. Okay. Now, after the first drop, we've seen you get this spitting. So tip streaming is something, if you put a drop in a shear flow, so the way they do this is with a roller. So you basically have four rollers which look like this. So they give rise to a local shear. And then so from the distortion you get from the resulting flow, the distortion of the drop you can measure, say, its surface tension, right? Because the surface tension is resisting its deformation due to viscous stresses. And they find that at very high shear rates, the drop goes unstable and starts ejecting little droplets. If there's surfactants around there, it's called tip streaming. So they try to rationalize this in terms of tip streaming, but I still don't really understand it. It's no good just to give you solved problems. It's good to throw a few ridiculous ones in there. Okay, let's take a break. But don't. Okay. Can we stop the camera for a second? Can we stop the